Look up at the night sky, and what do you see? A breathtaking dance of light and shadow, where some stars form perfect geometric patterns, while others explode in unpredictable bursts of energy. This cosmic ballet isn't just beautiful, it's one of the universe's deepest mysteries. How can something so chaotic also be so perfectly ordered? The answer lies in the delicate balance between symmetry and chaos, two forces that shape everything from the tiniest atoms to the largest galaxies. Think about it. The same mathematical rules that keep planets orbiting in precise harmony also allow for the violent storms of Jupiter or the swirling chaos of a black hole. It's as if the universe is both an artist and a rebel, painting with perfect brushstrokes one moment and throwing paint at the canvas the next. For centuries, scientists and philosophers have been captivated by this paradox. Why does nature seem to follow hidden rules while also embracing randomness? Take the spiral arms of a galaxy. They're stunningly symmetrical, yet within them, stars are born and die in chaotic explosions. Or consider the way snowflakes form. No two are alike, yet each one obeys the same geometric principles. This isn't just a quirk of physics, it's a clue to something far bigger. The interplay of symmetry and chaos might hold the key to understanding how the universe began, how it evolves, and even what fate awaits it billions of years from now. So what's really going on out there? Why does the cosmos cling to order in some places and revel in disorder in others? That's the journey we're about to take together. We'll explore how black holes warp space and time, how quantum particles defy predictability, and how the very fabric of reality might be woven from both precision and pandemonium. Along the way, we'll uncover startling discoveries that blur the line between science and philosophy, because this isn't just about distant stars and galaxies. It's about unraveling the blueprint of existence itself, so buckle up. By the end of this, you'll never look at the night sky the same way again. Symmetry isn't just something we admire in art or nature, it's woven into the very fabric of reality. Take a snowflake, for example. Under a microscope, you'll see a dazzling six-fold symmetry, each branch perfectly mirrored. But zoom out to the scale of galaxies, and you'll find the same principle at work. The spiral arms of the Milky Way aren't random, they're shaped by gravitational forces that create stunning, repeating patterns. Even the tiniest building blocks of matter, like atoms, follow symmetrical arrangements. Electrons orbit nuclei in predictable shells, and crystals form lattices so precise we can use them to measure time in atomic clocks. This obsession with symmetry isn't just a cosmic coincidence, it's a clue to how the universe operates. Physicist Emmy Noether made one of the most profound discoveries in science when she proved that every symmetry in nature corresponds to a conservation law. Time's symmetry, the fact that physical laws don't change from moment to moment, means energy is always conserved. Space's symmetry, the idea that physics works the same here as it does in a distant galaxy, ensures momentum stays constant. These aren't abstract ideas, they're the rules that keep planets in orbit, stars burning, and even your coffee from spontaneously flying off the table. Yet, if symmetry is so powerful, why isn't everything perfectly uniform? Why do galaxies have messy, chaotic regions alongside their elegant spirals? The answer lies in the tension between order and randomness. Symmetry provides the blueprint, but chaos fills in the details. When the universe began, the Big Bang unleashed near-perfect symmetry, but as matter cooled and clumped together, tiny imperfections grew. Gravity amplified these differences, creating the cosmic web of galaxies we see today. Even in something as simple as a snowflake, no two are truly identical because chaos always leaves its mark. This delicate balance between symmetry and disorder might be the key to understanding why the universe is so diverse. Without symmetry, there would be no structure, just endless randomness. But without chaos, there would be no stars, no planets, no life. The universe seems to thrive on this interplay, using symmetry as a scaffold and chaos as the artist's brush. And if we look closely enough, we might just find that what appears random is simply symmetry unfolding in ways we're only beginning to understand. Chaos might seem like the opposite of symmetry, but in reality, these two forces work together in ways that shape the very universe we live in. Picture a spinning top, perfectly balanced at first, its motion smooth and predictable, but give it the slightest nudge and suddenly it wobbles, teeters, and finally topples. That's chaos theory in action, a system so sensitive to initial conditions that even the tiniest change can lead to wildly different outcomes. Now scale that idea up to cosmic proportions. Jupiter's Great Red Spot, a storm larger than Earth, has churned for hundreds of years not despite chaos, but because of it. The same turbulent forces that create unpredictable weather patterns here on Earth also sculpt the swirling bands of gas giants and the violent births of stars in distant nebulae. What makes chaos so fascinating is that it's not random, it follows rules, just like symmetry does. Take the orbits of asteroids in our solar system. While planets move in near-perfect ellipses, thanks to gravity's predictable pull, asteroids in the belt between Mars and Jupiter are a different story. Their paths are chaotic, influenced by the tiniest gravitational tugs from nearby rocks or planets. Over millions of years, these small nudges can send an asteroid spiraling toward Earth or flinging it out into deep space. This isn't luck or chance, it's the universe's way of balancing precision with unpredictability. Even in the quantum realm, particles behave in ways that defy absolute certainty, their positions and momentums governed by probabilities rather than fixed paths. So how does chaos fit into the grand cosmic design? Think of it like a painter who starts with a perfectly symmetrical sketch, but then adds bold, unpredictable strokes to bring it to life. Without chaos, the universe would be static, a frozen sculpture of mathematical perfection. But with it, we get supernova exploding in brilliant flashes, galaxies colliding in spectacular mergers, and even the delicate dance of Decay folding in ways that give rise to life. The same forces that create hurricanes on Neptune might have shaped the early conditions that allowed our solar system to form. Chaos doesn't destroy order, it reshapes it, revealing hidden patterns we're only beginning to decode. This delicate interplay raises an even bigger question. Could chaos be the universe's way of innovating? If everything followed rigid symmetry, there'd be no diversity, no evolution, no surprises. But with chaos in the mix, the cosmos becomes a dynamic, ever-changing tapestry. Stars explode, scattering elements that form new planets. Solar systems wobble, flinging comets into the void. Even Earth's climate, with its ice ages and warming periods, is a product of chaotic feedback loops. Far from being destructive, chaos might just be the universe's most creative force, the wild card that keeps the story of existence endlessly fascinating. The universe operates like a grand pendulum, constantly swinging between harmony and upheaval. Gravity's invisible hand sculpts planets into neat orbital paths, while dark energy stretches the cosmos apart with relentless force. Picture Saturn's iconic rings from afar. They appear as flawless concentric circles, a masterpiece of celestial symmetry. But peer closer, and you'll find a frenzied dance of ice and rock, where particles collide, shatter, and reform in endless chaos. This duality isn't a flaw, it's the universe's signature. Even the forces governing atoms play this game. Electromagnetism binds electrons to nuclei in precise, repeating shells, creating the stable matter that builds everything from stars to smartphones. Yet entropy, nature's unstoppable trend toward disorder, ensures no system stays perfectly tidy. A cup of coffee cools, stars exhaust their fuel, and even black holes, those perfect spheres of warped spacetime, are surrounded by swirling accretion disks hotter than a supernova. Scientists call this delicate equilibrium self-organized criticality, a state where systems teeter on the edge of stability, like a sand pile moments before an avalanche. One grain too many and the entire structure shifts. This tension might explain why the cosmos thrives instead of crumbling. After the Big Bang, the universe was a seething plasma of near-perfect symmetry. But as it expanded and cooled, tiny quantum fluctuations grew into galaxies, like wrinkles in a stretching canvas. Without those imperfections, matter would have spread evenly, leaving a cold, featureless void. Instead, gravity amplified the slightest variations, weaving the cosmic web we see today. Chaos didn't disrupt the design, it made the design possible. The implications stretch beyond astronomy. Life itself depends on this balance. DNA's double helix is a marvel of symmetry, yet mutations, random errors in its code drive evolution. Earth's climate balances solar input and radiative cooling, but chaotic feedback loops create storms, droughts, and ice ages. Even our brains rely on orderly neural networks punctuated by bursts of unpredictable creativity. The universe doesn't choose between order and chaos, it harnesses both. And if we listen closely, the cosmos might be whispering that perfection isn't the goal. It's the interplay between stability and surprise that keeps the story alive. Imagine the universe in its infancy, a seething, ultra-hot soup where all forces were one, and particles moved without mass like dancers in perfect unison. This was a realm of pure symmetry where no direction, no particle, no force stood apart from another. But perfection, it turns out, was fleeting. As the cosmos expanded and cooled, something extraordinary happened. Like water freezing into ice, the universe underwent phase transitions, sudden shifts that shattered its pristine symmetry. These cosmic cracks didn't just create flaws, they birthed the diversity that defines existence. Take the Higgs field, an invisible energy blanket stretching through space. When the universe cooled past a critical temperature, this field activated like a switch, giving particles mass and breaking what physicists call electroweak symmetry. Before this moment, photons and W and Z bosons were indistinguishable, same energy, same behavior. Afterward, they split into distinct entities, massless photons carrying light, and heavy bosons governing weak nuclear forces. This wasn't just a tiny adjustment. It was a revolution that made atoms, chemistry, and life possible. Without this break in symmetry, electrons would zip around at light speed, never binding to nuclei. Stars wouldn't ignite, galaxies wouldn't form, but the story doesn't end there. These symmetry breaks left behind cosmic fingerprints, defects in spacetime itself. Picture a frozen lake cracking as temperatures drop. The ice is still crystalline, but the fractures create unique patterns. Similarly, as the universe cooled, tangled loops of energy called cosmic strings may have formed, stretching across light years. Other defects, like magnetic monopoles or domain walls, could have emerged, sculpting the distribution of matter. Some theories suggest these imperfections acted as gravitational seeds, pulling gas into the first galaxies. What we once called flaws might be the very reason we exist. Even time's relentless march toward disorder stems from this broken symmetry. The early universe was so uniform that time could have flowed backward or forward without consequence. But as symmetries fractured, entropy found its arrow. Now, spilled milk never unspills, and stars burn irreversibly toward collapse. This asymmetry isn't a bug, it's the feature that makes cause and effect, memory, and even consciousness possible. So why did the universe trade perfection for imperfection? Perhaps because symmetry, while beautiful, is sterile. A perfectly symmetrical cosmos would stay forever uniform, unchanging, and lifeless. By embracing asymmetry, the universe gained texture: mountains and valleys, stars and voids, order and chaos dancing together. It's as if existence itself chose creativity over conformity, weaving a tapestry so rich that we're still unraveling its threads billions of years later. And somewhere in those ancient cracks, we might just find the answer to why anything exists at all. Fractals are nature's hidden masterpiece, a perfect marriage of symmetry and chaos where patterns repeat endlessly, yet no two moments are ever quite the same. Picture a snow-covered mountain range from high above. The jagged peaks and valleys mirror the rough edges of a single snowflake under a microscope. Zoom in further, and you'll find the same irregular elegance in the branching veins of a leaf or the twisting path of a river delta. This isn't just a visual coincidence, it's a fundamental blueprint woven into the fabric of reality. The universe doesn't just tolerate chaos, it sculpts it into something breathtakingly structured. Take the cosmic web, for instance. From a distance, the distribution of galaxies looks like a delicate lattice, threads of matter stretching across the void in a vast, interconnected network. But up close, each thread is a turbulent river of stars, gas, and dark matter, clumping and splitting in ways that defy simple geometry. This isn't random, it's fractal. The same forces that shape the branching of a tree or the cracks in drying mud also govern the large-scale structure of the universe. Mathematician Benoit Mandelbrot called these patterns roughness, but they're anything but messy. They're precise in their unpredictability, governed by simple mathematical rules that generate infinite complexity. Even the surfaces of stars tell this story. Our sun may look like a smooth orb from Earth, but its outer layers churn with plasma in fractal-like turbulence, magnetic fields twisting and snapping, creating flares that reach thousands of miles into space. These eruptions follow no strict timetable, yet their shapes echo the branching forks of lightning or the jagged edges of a shattered pane of glass. It's as if the universe has a favorite recipe: take a dash of order, a sprinkle of chaos, and repeat. What makes fractals so extraordinary is how they blur the line between the predictable and the unpredictable. A coastline measured with a yardstick will give one length, but measure it with a ruler that accounts for every tiny inlet and pebble, and the distance grows infinitely. This isn't a flaw in measurement, it's a feature of reality. The universe refuses to be pinned down to a single scale, revealing new layers of complexity the closer we look. Could this be the secret language of the cosmos, a way to encode both structure and spontaneity into the same equation? From the spiral arms of galaxies to the neural networks in our brains, fractal geometry seems to be nature's favorite tool for building complexity out of simplicity. And if that's true, then chaos isn't the absence of order. It's order in disguise, waiting for us to decipher its patterns. The more we explore, the clearer it becomes. The universe isn't choosing between symmetry and chaos. It's using both to write its grandest story. Dark matter is the universe's silent architect, shaping the cosmos with an invisible hand. We can't see it, touch it, or detect it directly, yet without its gravitational pull, galaxies would spin themselves apart like unmoored carousels. Think of it as the scaffolding behind a grand construction project, hidden from view but holding everything together. Across the vast expanse of space, dark matter weaves galaxies into sprawling filaments, creating a cosmic web so precise it resembles the branching veins of a leaf. But here's the twist: while this web appears orderly on a colossal scale, zoom in closer and you'll find a universe of chaos. Dark matter doesn't spread evenly like butter on toast. It clumps and clusters in unpredictable ways, forming halos around galaxies with intricate, fractal-like substructures. These halos aren't smooth or uniform. Instead, they're more like cosmic spiderwebs, with dense knots and wispy threads tangled together. Supercomputer simulations show dark matter as a dynamic, ever-shifting entity, where tiny fluctuations in the early universe snowballed into the vast structures we see today. One region might collapse into a galaxy cluster weighing a quadrillion suns, while another remains eerily empty, a void stretching millions of light years. This interplay between symmetry and randomness is what makes dark matter so fascinating. It's not just glue holding galaxies together. It's an active participant in the universe's dance, shaping both order and chaos simultaneously. Yet for all its influence, dark matter remains one of science's greatest mysteries. We know it exists because of its gravitational effects. Stars orbit galaxy centers too fast to be held by visible matter alone, and light bends around invisible mass in ways Einstein predicted. But what is it? Is it a sea of exotic particles too shy to interact with light? Could it be primordial black holes, remnants of the Big Bang lurking in the shadows? Or something even stranger beyond our current physics? Laboratories deep underground, particle colliders, and space telescopes are all hunting for clues, each experiment peeling back another layer of this cosmic enigma. The search for dark matter isn't just about filling in a gap in our equations, it's about understanding the universe's blueprint. If symmetry is the rulebook and chaos the wild card, dark matter might be the referee, quietly enforcing the game. Its elusive nature challenges us to rethink what we know about matter, energy, and the very fabric of reality. And with every new discovery, we're reminded that the cosmos loves a good paradox. The most powerful forces are often the ones we can't see. Dive into the heart of an atom, and you won't find neat little planets orbiting a nucleus. You'll step into a storm. This is the quantum foam, a seething, bubbling ocean where particles flicker into existence and vanish faster than a blink. Imagine space itself as a restless sea with waves constantly cresting and collapsing. Here, the rules of the everyday world don't apply. Particles pop up from nothing, borrowing energy from the universe in fleeting violations of the laws of physics. But before you can even measure them, they're gone again, paying back their energy debt in a cosmic game of now you see it, now you don't. This chaos isn't random. It's governed by Heisenberg's uncertainty principle, a fundamental rule that says you can never precisely know both where a particle is and how fast it's moving. The more you pin down one, the more the other slips through your fingers. It's like trying to catch smoke with your hands. The tighter you squeeze, the more it escapes. This isn't a limitation of our tools. It's baked into the fabric of reality. At the quantum level, the universe thrives on ambiguity, trading certainty for a vibrant, dynamic instability that somehow gives rise to the solid world we experience. Yet, amid this subatomic frenzy, there's a hidden order. Virtual particles, those fleeting guests in the quantum foam, seem to break symmetry with their spontaneous appearances. But when you zoom out, their net effects obey strict, unbreakable laws. The chaos cancels itself out, leaving behind the stable forces that hold atoms together. It's as if the universe is a master accountant, balancing its books so precisely that the temporary debts of virtual particles never upset the grand ledger. This delicate dance of disorder and harmony is what keeps electrons in their orbits, prevents atoms from collapsing, and ultimately makes matter possible. So how does this microscopic pandemonium shape the cosmos? The answer lies in the vacuum of space itself, which isn't empty at all. It's a roiling soup of quantum activity, where particles and antiparticles constantly duel in fleeting bursts of energy. Even in the darkest void, this quantum turbulence generates tiny forces like the Casimir effect, where two metal plates placed incredibly close together feel an invisible push from the particles winking in and out around them. On a grander scale, these quantum fluctuations might have seeded the first structures in the universe, amplifying tiny ripples into galaxies and clusters. The paradox only deepens as we pull back. The same quantum unpredictability that defies symmetry at the smallest scales creates the stability we see in stars, planets, and even life. It's a reminder that chaos isn't the enemy of order. It's the raw material from which order emerges. The universe doesn't just tolerate uncertainty, it depends on it, weaving randomness into the very foundation of existence. And if we listen closely to the whispers of the quantum foam, we might just hear the universe's oldest secret. That perfection isn't found in stillness, but in the beautiful, turbulent dance between chance and necessity. Black holes are cosmic paradoxes, masters of symmetry and chaos rolled into one. Picture the event horizon, that invisible boundary where gravity becomes so strong not even light can escape. From the outside, it's a flawless sphere, a perfect embodiment of the no-hair theorem, which states that black holes can be described by just three simple features: mass, spin, and charge. No bumps, no wrinkles, no imperfections. It's as if the universe took a chaotic collapse of matter and smoothed it into the simplest geometric shape possible. But cross that horizon and the order unravels. Space-time twists into knots, stretching and compressing in ways that defy imagination. The laws of physics as we know them break down, and information, the very blueprint of what fell in, seems to vanish without a trace. Yet even here, in this realm of extremes, symmetry and chaos dance together. Take Hawking radiation, the eerie glow that black holes emit over time. Quantum mechanics tells us that particle-antiparticle pairs constantly flicker into existence near the event horizon. Normally, they annihilate each other in an instant, but if one particle falls into the black hole while the other escapes, the whole loses energy and slowly evaporates. What's astonishing is how this chaotic quantum process produces something orderly, a steady stream of radiation that follows precise thermal laws. It's like watching a tornado tear through a library, only for the scattered pages to rearrange themselves into a new book. This paradox might hold the key to one of physics' biggest puzzles: how to reconcile Einstein's theory of gravity with quantum mechanics. Black holes straddle both worlds, warping spacetime while also obeying quantum rules. Some scientists think the event horizon acts like a hologram, preserving information in two dimensions that encodes the chaos within. Others suggest black holes are cosmic erasers, scrambling information so thoroughly that it reemerges in unrecognizable form. The debate rages on, but one thing's clear: black holes aren't just cosmic vacuum cleaners. They're laboratories where the universe tests its deepest laws, pushing order and disorder to their limits. And that's what makes them so fascinating. They're not just destroyers, they're creators too. The same violent forces that rip matter apart might also seed new structures. Some theories propose that black holes could birth entire universes inside their cores, where crushed spacetime rebounds in a new Big Bang. Others suggest their evaporation leaves behind strange remnants, like Planck-sized nuggets of pure information. Whether they're gateways, holograms, or something we haven't even imagined, black holes remind us that the universe doesn't play by binary rules. It thrives in the gray areas where symmetry and chaos collide, and where the next great discovery might be hiding just beyond the event horizon. When a massive star reaches the end of its life, it doesn't fade quietly. It goes out with a bang so powerful it can outshine entire galaxies. A supernova is nature's ultimate paradox, a cataclysm of destruction and creation wrapped into one blinding flash. At its core, chaos reigns supreme. Temperatures soar beyond billions of degrees, atoms are smashed together with unimaginable force, and shockwaves ricochet through the star's collapsing layers like cosmic pinballs. There's nothing orderly about this process. It's a free-for-all where protons, neutrons, and electrons are forged into heavier elements in a frantic nuclear frenzy. Iron becomes gold, carbon transforms into uranium. In mere seconds, the star's core becomes a factory for the building blocks of planets, life, and even the device you're watching this on right now. Yet from this pandemonium emerges something astonishingly precise. The explosion doesn't just spew debris randomly, it sculpts the ejected material into vast, symmetrical shells that expand outward like perfectly timed ripples in a pond. These shockwaves travel at millions of miles per hour, sweeping up interstellar gas and dust, triggering the birth of new stars in their wake. The Crab Nebula, remnants of a supernova witnessed in the year 1054, still glows with intricate, lace-like filaments, a testament to how chaos can give rise to breathtaking order. This isn't just a stellar spectacle, it's a cosmic necessity. Without supernova, the universe would be a barren wasteland of hydrogen and helium. There'd be no oxygen to breathe, no calcium for bones, no silicon for computer chips. Every heavy element in your body was forged in the heart of a dying star and scattered across the cosmos by these violent explosions. Even Earth's gold and platinum likely arrived via ancient supernova debris, delivered billions of years ago before our solar system took shape. But the story doesn't end there. Supernova are the architects of structure on the grandest scales. Their shockwaves compress interstellar clouds, nudging them past the tipping point where gravity takes over, collapsing them into new stellar nurseries. Some theories suggest that the shock fronts from multiple supernova can even shape galaxies, carving out vast bubbles in the interstellar medium that channel star formation into spirals and rings. It's as if the universe uses these explosions like chisels, sculpting chaos into the frameworks that build everything else. And perhaps most remarkably, supernova follow a hidden script. Despite their unpredictability, they adhere to strict physical laws that allow astronomers to use them as standard candles, cosmic yardsticks, to measure the expansion of the universe itself. The same explosions that seem to defy order end up revealing the universe's deepest symmetries. So next time you look up at the night sky, remember, the same forces that tear stars apart are the ones that built the world beneath your feet. The universe doesn't just tolerate chaos, it depends on it to create. Stretching across billions of light years, the cosmic web is the universe's grandest architectural feat. A sprawling labyrinth of galaxies, gas, and dark matter woven into filaments so vast they defy comprehension. Picture the roots of a colossal tree, branching endlessly through the soil of space-time, each tendril pulling matter into its embrace. These filaments aren't random scribbles, they're gravity's masterpiece, tracing the hidden blueprint of the cosmos. Yet for all their symmetry, these threads are anything but static. Dark energy tugs at them like an invisible tide, stretching the web thinner even as gravity fights to hold it together. The result, a dynamic, ever-shifting structure where order and chaos are locked in an eternal tug of war. What's astonishing is how familiar this pattern feels. The cosmic web mirrors the neural networks in our brains, with galaxies clustered like neurons at the intersections of filaments. Some scientists suggest this isn't just a visual coincidence. It might hint at deeper universal principles. Just as thoughts emerge from the electrical chatter of neurons, large-scale structures in the universe could arise from similar rules of connection and feedback. Supercomputer simulations reveal that the web evolves like a living system, with matter flowing along filaments like nutrients through veins, feeding galaxy clusters at the nodes. These clusters, the web's densest knots, act as cosmic metropolises, humming with the energy of colliding gas and merging black holes. But the real magic lies in the voids, the web's empty spaces. These aren't just gaps, they're active players in the cosmic dance. As dark energy accelerates the expansion of the universe, voids grow like bubbles in rising dough, pushing filaments into sharper relief. Some stretch hundreds of millions of light years across, so devoid of matter that if you stood in one, the night sky would appear nearly black. Yet even here, chaos has purpose. The pressure difference between voids and filaments drives winds of intergalactic gas, seeding new star formation along the web's edges. It's a reminder that emptiness isn't passive, it sculpts the universe as much as matter does. Could this web be processing information like some kind of cosmic computer? The idea isn't as far-fetched as it sounds. Every interaction, every galaxy collision, every burst of star formation leaves an imprint on the web's structure, a ripple in the gravitational field. Some theorists propose that the universe might be a self-organizing system, where complexity emerges from simple rules, much like cells forming a body or ants building a colony. The more we map the web, the more it seems to follow mathematical patterns seen in everything from fluid dynamics to the growth of slime molds. Nature, it seems, has a favorite toolkit, and the universe is no exception. Peering into this vast network, we're not just mapping space, we're unraveling the universe's operating system. Each filament, each void, each shimmering galaxy is a line of code in a program written 13.8 billion years ago. And as we decode it, we might just discover that the cosmic web isn't just the universe's skeleton, it's its heartbeat, pulsing with the rhythm of creation itself. Why does the universe seem tailor-made for life? Look around: the air you breathe, the ground beneath your feet, even the screen you're staring at. All of it exists because the cosmos struck an impossible balance between rigidity and randomness. This is the anthropic principle in action, the idea that the universe's fundamental constants and laws aren't arbitrary. They're fine-tuned to a razor's edge, allowing atoms to bond, stars to shine, and planets to cradle life. Take the fine structure constant, a number governing how tightly electrons cling to atomic nuclei. If this value were even slightly different, chemistry as we know it would collapse. Carbon, the backbone of life, wouldn't form in stellar furnaces. Water molecules wouldn't exhibit their unique properties. The universe would either be a frozen wasteland or a chaotic plasma, no in-between. But here's what's even more astonishing. This balance isn't static. It's dynamic, like a cosmic tightrope walker, constantly adjusting to stay upright. Gravity, for instance, is strong enough to pull gas clouds into stars, but weak enough that those stars don't instantly crumple into black holes. The nuclear forces binding atoms are potent enough to forge heavy elements in supernova, but not so overpowering that they prevent radioactive decay, a process crucial for Earth's geothermal heat, and even the mutations driving evolution. Even the expansion rate of the universe plays a role. Too fast, and matter would never clump into galaxies. Too slow, and everything would collapse back into a singularity before life could blink into existence. This delicate equilibrium raises a provocative question. Is consciousness an inevitable outcome of these Goldilocks conditions? Some scientists argue that the universe's laws aren't just compatible with life, they're biased toward it. The same symmetries that dictate particle physics might also underpin the emergence of self-aware beings capable of pondering their own existence. After all, the carbon in your cells, the iron in your blood, and the calcium in your bones were all forged in the hearts of dying stars. You're not just observing the universe, you're a product of its most precise calculations. Yet not everyone agrees. Critics of the anthropic principle call it a tautology. Of course, we observe a life-friendly universe. We couldn't exist in one that wasn't. But even this perspective misses the deeper mystery. Why does any life-permitting universe exist at all? The sheer improbability of so many constants aligning just right suggests something extraordinary. Maybe there are infinite universes, each with different laws, and we simply inhabit the one where the dice rolled in our favor. Or perhaps symmetry and chaos aren't opposing forces, but partners in a grander scheme we're only beginning to glimpse. One thing's certain, the universe's recipe for life relies on both precision and flexibility. Too much symmetry, and everything locks into sterile perfection. Too much chaos and structure dissolves into noise, but in that narrow band between them, galaxies spin, planets coalesce, and life emerges, not as an accident but as a cosmic inevitability. So the next time you gaze at the stars, remember, you're not just a speck in the void. You're proof that the universe knows how to walk the line between order and chaos, and that, in itself, might be the greatest symmetry of all. Time moves forward, that's the one rule we think can't be broken. Eggs don't unscramble, shattered glass doesn't leap back into place, and stars burn out without reigniting. This relentless march toward disorder is entropy in action, the universe's way of trading neatness for unpredictability. But what if time's arrow isn't as straight as it seems? Some theories suggest the cosmos might be caught in an endless loop, where collapse and rebirth dance in an eternal cycle. Imagine a pendulum swinging between order and chaos, where every big bang is followed by a big crunch, a cosmic inhale to match the exhale. In this view, the universe isn't racing toward heat death. It's simply pausing before the next act begins. Black holes offer a tantalizing clue to this paradox. These cosmic vacuum cleaners suck in matter and energy, creating pockets of maximum entropy where information seems to vanish. Yet, on a grand scale, they preserve symmetry, their event horizons perfect spheres, their gravitational pull obeying precise mathematical laws. It's as if they're microcosms of the universe itself, chaotic within, orderly without. Even Hawking radiation, the slow leak of energy from black holes, hints at a deeper balance. The particles escaping carry away entropy, redistributing it into the cosmos like seeds scattered by the wind. Could this be nature's way of recycling disorder, preparing the stage for a fresh start? The idea of cyclical time isn't new. Ancient Hindu cosmology spoke of universes breathing in and out over trillions of years, while modern physics toys with the Big Bounce, a model where the universe contracts to a single point before exploding outward again. Each cycle would reset entropy, erasing the cosmic ledger clean. But here's the twist, even in these models, something lingers. Quantum fluctuations from the previous cycle might imprint on the next, like echoes in a cosmic canyon. The universe wouldn't just repeat, it would evolve, carrying forward whispers of its past. So which is it, a one-way slide into chaos or an endless waltz of order and disorder? The answer might lie in the fabric of space-time itself. Dark energy, the mysterious force accelerating the universe's expansion, could be the deciding factor. If it weakens over time, gravity might eventually pull everything back together. If it holds steady, the cosmos will keep stretching into cold, empty silence. Either way, entropy isn't just a force of destruction. It's the engine of change, the reason stars shine and life evolves. The universe may not care about neatness, but it thrives on transformation. And if eternity is real, it's not a static forever. It's a story written and rewritten in the language of symmetry and chaos. Imagine plucking a guitar string. The vibrations create distinct musical notes, each one a unique harmony. Now picture that same principle governing the fundamental building blocks of reality. String theory suggests that every particle in the universe, from the tiniest quark to the mightiest photon, isn't a point but a microscopic, vibrating string. The pitch of these vibrations determines whether a string manifests as an electron, a quark, or even a carrier of gravity. It's a breathtaking idea. The entire cosmos might be a grand symphony, with the laws of physics composed by the resonant frequencies of these invisible threads. But there's a catch. For the math to work, these strings can't just wiggle in the 3 dimensions we know. They need room to dance. That's where Calabi-Yau manifolds come in. These intricate, 6-dimensional shapes are so complex they defy visualization, twisting and folding in ways that make M.C. Escher's drawings look like child's play. Hidden within these geometric labyrinths, strings could vibrate in countless patterns, each one corresponding to a different particle or force. It's as if the universe's rulebook is written in a language of higher dimensional origami, where symmetry isn't just beautiful, it's the glue holding reality together. Yet for all its elegance, string theory has a chaotic side. The same equations that demand exquisite symmetry also predict a staggering 10 to the power of 500 possible universes, each with its own unique physics. Some might have stronger gravity, others no electrons, and a rare few, like ours, might strike the perfect balance for stars, planets, and life. This landscape of possibilities raises a profound question. Is our universe special, or just one accidental melody in a cacophony of cosmic possibilities? The search for answers is pushing science to its limits. Particle colliders like the Large Hadron Collider hunt for evidence of extra dimensions or supersymmetry, a key prediction of string theory that pairs every known particle with a heavier twin. Meanwhile, mathematicians dissect Calabi-Yau shapes for clues about why our universe's particular vibration rose to dominance. But the biggest challenge remains string theory is so flexible it's hard to disprove, and without experimental proof, it walks the line between groundbreaking science and metaphysical speculation. What's undeniable is the theory's audacious vision. It doesn't just unify gravity and quantum mechanics, it suggests that the universe's deepest truths might be written in vibrations, hidden dimensions, and geometries beyond human intuition. Whether string theory ultimately proves right or wrong, it's reshaped how we think about symmetry and chaos, showing that even in the most abstract corners of physics, the universe still dances to the same timeless rhythm. Dark energy is the universe's greatest enigma, a phantom force pushing galaxies apart faster than gravity can pull them together. Picture a runaway balloon, inflating so rapidly that dots on its surface streak away from one another, their connections stretching thin. That's our cosmos in a nutshell, an accelerating expanse where clusters of galaxies will one day vanish beyond an unreachable horizon, their light too faint to ever reach us again. What's baffling isn't just the speed of this expansion, but its eerie uniformity. Unlike gravity, which clumps matter into galaxies and stars, dark energy exerts the same repulsive pressure everywhere, as if space itself has a built-in anti-gravity symmetry. But here's where the paradox deepens. This uniformity isn't passive, it's actively reshaping the cosmic landscape. Voids between galaxies grow like bubbles in boiling water, while filaments of the cosmic web strain against the pull of dark energy's relentless push. The result, a universe where structure and chaos are locked in a tug of war. On one hand, dark energy smooths things out, Chinese letter, the density of matter across ever larger volumes of space. On the other, it amplifies the contrast between the nearly empty voids and the dense galaxy clusters clinging to the web's nodes. It's as if the cosmos is being ironed flat while simultaneously fraying at the edges. The leading theory pins dark energy on the cosmological constant, a term Einstein once added and later discarded in his equations to keep the universe static. Today, it's resurrected as the energy of empty space itself, a constant hum of repulsion woven into the vacuum, but cracks are appearing in this tidy explanation. Measurements of the universe's expansion rate don't quite line up between nearby galaxies and distant supernovae. Some data hints that dark energy might not be constant at all. It could evolve, growing stronger or weaker over time. If true, this would upend our understanding of cosmic fate. A strengthening dark energy could rip apart galaxies, stars, and even atoms in a big rip. A fading one might let gravity regain dominance, collapsing everything back into a fiery crunch. What's most striking is how dark energy mirrors the universe's broader theme, chaos disguised as order. Its effects appear uniform, yet its origin remains shrouded in quantum uncertainty. Some theories suggest it's tied to fleeting particle-antiparticle pairs popping in and out of the vacuum, a chaotic process yielding a strangely symmetric outcome. Others propose it's a new fundamental force, or even a sign we've misread gravity's rules. Whatever the answer, dark energy reminds us that the cosmos thrives on contradiction. It expands with perfect symmetry, yet that very expansion fuels the chaos of isolation, where galaxies become islands in an ever-darkening sea. The universe, it seems, loves its paradoxes, and dark energy might just be the ultimate wild card in the deck. What if our universe isn't the only one? Imagine a cosmic library with endless shelves, each holding a different universe with its own unique set of rules. In some, gravity might be 10 times stronger, crushing matter into black holes the size of marbles. In others, electromagnetism could be so weak that atoms never bond, leaving space a vast, lifeless haze. This is the multiverse theory, a mind-bending idea that every possible combination of physical laws and initial conditions plays out somewhere in a grand, infinite ensemble. And nestled among them all is our peculiar universe, where symmetry and chaos strike that improbable balance, allowing galaxies, planets, and conscious beings to exist. The implications are staggering. In a multiverse, universes could range from rigidly ordered realms, where stars align in perfect geometric grids and time ticks with metronome precision, to realms of pure anarchy, where matter swirls in endless, unstructured turbulence. Ours sits somewhere in between, with just enough chaos to spark supernova and just enough symmetry to keep atoms stable. But here's the twist: if countless universes exist, does ours feel special because it's truly unique, or simply because we're here to observe it? This is the Anthropic principle in overdrive, a cosmic version of survivorship bias where we're only around to ponder the question because the conditions allowed it. Philosophers and theologians have wrestled with this for centuries. Is the fine-tuning of our universe evidence of a deeper design, or just a statistical inevitability in an infinite sea of possibilities? Some physicists argue that the multiverse could explain why fundamental constants like the strength of gravity or the mass of an electron appear so exquisitely balanced for life. If every value is tried somewhere, it's no surprise we find ourselves in a universe where the numbers line up just right. Others push back, insisting that invoking infinite unseen worlds is a cop-out, a way to dodge the harder question of why this universe exists as it does. Cutting-edge science is now probing the edges of this debate. Cosmic microwave background anomalies, mysterious cold spots, and unusual patterns in the afterglow of the Big Bang have sparked speculation that they could be bruises from collisions with other bubble universes. String theory's landscape of possible vacuum states offers a mathematical framework for how different universes might emerge, each with its own physics. And quantum mechanics, with its many worlds interpretation, suggests that every quantum decision spawns branching realities where all possible outcomes occur. Yet the multiverse remains tantalizingly out of reach. Without a way to observe or interact with these other realms, the theory walks the line between science and metaphysics. But whether it's ultimately proven or not, the idea forces us to confront profound questions about our place in the cosmos. Are we the result of an unimaginable cosmic lottery, or is there something deeper at work? The multiverse doesn't just expand our notion of reality, it challenges us to rethink what it means to be special in an existence where everything that can happen does. Neutron stars are cosmic contradictions, smooth as polished marble on the outside, yet churning with unimaginable turbulence within. Picture a city-sized sphere so perfectly round that if you scaled it to the size of Earth, its tallest mountains would be no higher than a millimeter. Gravity here is a relentless sculptor, crushing matter so tightly that protons and electrons fuse into neutrons, packing the mass of a sun into a ball smaller than Manhattan. But beneath this flawless surface lies a storm. The core isn't just dense, it's a quantum maelstrom where neutrons flow like a frictionless superfluid, swirling in microscopic whirlpools that could stretch for miles. Then there's the crust, a brittle shell of iron nuclei squeezed into a crystalline lattice. When the star's insane rotation slows even slightly, this crust buckles in starquakes, cosmic earthquakes so violent they release more energy in a millisecond than our sun does in 100,000 years. These tremors ripple through the star's magnetic field, which can be 1 trillion times stronger than Earth's. That's where magnetars come in, neutron stars with magnetic fields so intense they twist spacetime itself. When these fields snap and reconfigure, they unleash gamma-ray flares capable of frying satellites halfway across the galaxy, a symmetrical magnetic field erupting in wildly asymmetric bursts. How can something so precise on the outside be so chaotic within? The answer lies in the extremes of physics. Neutron stars exist at the edge of what matter can endure, where gravity, quantum mechanics, and electromagnetism collide in ways we're still struggling to understand. Their perfect exteriors are a facade, a reminder that even in the cosmos, appearances can be deceiving. Inside, the rules we know break down. Neutrons pair up like dancers in a superfluid ballet, while protons form rivers of electricity that twist into microscopic tornadoes. It's as if the star can't decide whether to be a monument to order or a monument to chaos, so it chooses both. What's astonishing is how these stellar zombies teach us about the universe's hidden wiring. The way their crust vibrates during starquakes reveals secrets about the nature of ultra-dense matter, hints that could help us unlock the mysteries of quark-gluon plasmas or even stranger states that might exist inside black holes. Their magnetic fields act like cosmic laboratories, creating conditions so extreme they mimic the first moments after the Big Bang. And their precise spins, some rotate hundreds of times per second, serve as celestial clocks so accurate they rival atomic timekeeping on Earth. In the end, neutron stars are more than just dead suns. They're cosmic paradoxes, proving that symmetry and chaos aren't opposites, they're partners in a dance that shapes the universe. From their flawless silhouettes to their turbulent hearts, these stars remind us that perfection isn't about stillness. It's about balance, a fleeting moment where opposing forces find harmony in the chaos. And somewhere in that balance, the universe hides its deepest truths. Quantum entanglement is the universe's ultimate magic trick. Two particles so deeply linked that changing one instantly influences the other, no matter how far apart they are. Picture tossing a pair of gloves into opposite ends of the galaxy. Open the left glove and find it's right-handed, and instantly, without any signal or delay, the right glove becomes left-handed. This isn't science fiction. It's a fundamental feature of reality, one that even Einstein found so unsettling he dismissed it as spooky action at a distance. But decades of experiments have proven entanglement is real, leaving us with a paradox that defies classical intuition: perfect symmetry paired with irreducible randomness. How does it work? When particles like photons or electrons become entangled, they lose their individual identities, merging into a single quantum state. Measure one spin or polarization, and its partner snaps into the opposite state, no matter if they're a millimeter or a million light years apart. This mirroring happens faster than light could travel between them, as if space and time simply don't apply. The symmetry here is flawless, a cosmic ballet where every move is perfectly coordinated. Yet the moment you peek behind the curtain, chaos takes over. Before measurement, neither particle has a definite state. They exist in a haze of probabilities. The act of observing one doesn't just reveal its state, it creates it, collapsing the system into a random outcome. This duality makes entanglement the ultimate bridge between order and unpredictability. On one hand, it's the most synchronized phenomenon in nature, a testament to the universe's knack for hidden harmonies. On the other, it's a reminder that randomness isn't just noise, it's woven into the fabric of reality. Some theories suggest entanglement might even be the glue holding space-time itself together, with every particle in the universe subtly linked through an invisible web of quantum connections. If true, this would mean the cosmos isn't just a collection of separate objects, but a vast, interdependent network where symmetry and chaos constantly negotiate the rules. The implications are staggering. Quantum computers harness entanglement to perform calculations that would take classical machines billions of years, solving problems like drug discovery or cryptography in mere seconds. But here's the catch: entanglement is fragile. The slightest interference from the outside world, a stray photon, a vibration, even a stray magnetic field, can unravel these delicate links, a phenomenon called decoherence. It's as if the universe insists on keeping its spookiest secrets just out of reach, teasing us with glimpses of order before snatching it back into the quantum fog. So is entanglement the universe's way of balancing cosmic harmony with creative chaos? The answer might lie in the strange fact that entanglement doesn't transmit information faster than light. No messages, no signals, just an eerie correlation that defies explanation. This loophole preserves Einstein's relativity while still allowing particles to communicate in a way that transcends space and time. Perhaps entanglement isn't a bug in the system but a feature, a reminder that the universe operates on rules far stranger than we've dared to imagine. And if we ever unlock its full potential, we might not just revolutionize technology, we might finally glimpse the hidden logic that binds order and chaos into one seamless whole. At the heart of quantum mechanics lies a mystery that blurs the line between observer and observed the moment a particle's fuzzy cloud of possibilities snaps into concrete reality simply because we look. This observer effect turns our classical intuition on its head, suggesting that the act of measurement isn't just passive recording but active participation. Picture Schrödinger's famous cat, suspended between life and death until the box opens. The mathematics of quantum theory treats particles as waves of probability, smeared across space until an observation forces them to choose a position, spin, or momentum. What's astonishing isn't just the randomness of the outcome, but the fact that observation itself seems to mediate between symmetry's clean equations and chaos's dice rolls. This raises a provocative question. Could consciousness be more than a byproduct of physics? Could it be part of the machinery? Philosophers and physicists have wrestled with this for decades. The Copenhagen interpretation, championed by Niels Bohr, treats wave-function collapse as a mathematical tool without specifying what constitutes an observer. But alternative views like von Neumann-Wigner interpretation go further, proposing that conscious awareness might be the trigger that crystallizes quantum possibilities into actualities. It's a radical idea that the universe's deepest layer isn't just particles and forces, but something resembling perception itself. Enter panpsychism, the view that consciousness isn't exclusive to brains but is a fundamental feature of reality, like mass or charge. In this framework, even elementary particles might possess rudimentary experience, not thoughts or feelings, but some bare-bones form of subjectivity. When electrons decide which path to take in a double-slit experiment, perhaps they're not just obeying blind probabilities but engaging in a proto-observational act. The cosmos, then, wouldn't just contain consciousness, it would be built from it, with mind and matter as two sides of the same coin. Critics argue this veers into metaphysics, pointing out that detectors and cameras can collapse wave functions without human involvement. Yet the boundary remains fuzzy. Quantum decoherence, where particles lose their quantum weirdness by interacting with their environment, offers a physical explanation for collapse, but still leaves open why one outcome manifests over another. Some theorists suggest a spectrum of observation where complexity matters. A photon hitting a photographic plate might count as a measurement, but a conscious mind perceiving the result could represent a deeper tier of reality making. What's undeniable is how this dance between observation and existence mirrors the universe's broader themes. Just as symmetry provides the stage and chaos writes the script, consciousness, if it plays a role, could be the audience that brings the performance to life. Whether we're passive witnesses or active participants, the quantum world insists we're not separate from the systems we study. We're entangled with them, collaborators in a cosmos where perceiving might just be another form of creating. Look at your hands mirror images of each other, down to the last knuckle and fingernail. This symmetry isn't just a quirk of human anatomy, it's a universal signature of life on Earth. From the spiral arms of seashells to the six-fold symmetry of snowflakes, biology adores patterns. Even the tiniest organisms, like radiolarians, construct their microscopic skeletons with geometric precision, as if following some cosmic blueprint. Yet beneath this elegant order lies a delicious paradox. Life's greatest innovations spring from chaos. Every time a cell divides, random mutations scramble the genetic script typos in DNA that could spell disaster or become the raw material for evolution's next masterpiece. Take the humble Escherichia coli, a bacterium so well studied it's practically biology's lab rat. In a single milliliter of liquid, millions of these tiny organisms swim, each one a near-perfect copy of the next. But introduce a stressor, say an antibiotic, and chaos takes the wheel. Random mutations make some bacteria resistant while others perish. The survivors pass their lucky genes to the next generation, reshaping the population in real time. This isn't just adaptation, it's a microscopic rebellion against entropy where disorder becomes the engine of order. Now zoom out to the grand theater of evolution. The double helix of DNA, with its elegant, ladder-like symmetry, seems like nature's ultimate ode to precision. Yet the very machinery that copies this helix, DNA polymerase, makes mistakes. About 1 in every billion base pairs gets misread, a tiny error that might vanish unnoticed or rewrite an organism's fate. These mutations are the universe's way of rolling the dice, and without them, life would be frozen in time. No finches diversifying on the Galapagos, no whales returning to the sea, no humans pondering the stars. Astrobiologists are obsessed with this balance. If symmetry provides stability and chaos fuels change, could the same recipe cook up life beyond Earth? They hunt for clues in extremophiles organisms thriving in places once deemed uninhabitable. Tube worms pulsating near hydrothermal vents, tardigrades surviving the vacuum of space, algae blooming in Antarctic ice. These creatures don't just endure chaos, they harness it, proving that life's playbook might work anywhere the universe offers energy and a pinch of randomness. And then there are exoplanets, worlds like Kepler 186f, orbiting in the habitable zone of distant stars, could be testing this equilibrium right now. Does their chemistry favor symmetrical molecules like Earth's amino acids? Do their tectonic plates churn unpredictably, stirring the pot of evolution? The answers could reveal whether life is a cosmic fluke or an inevitable outcome of nature's dance between symmetry and chaos. After all, if DNA's elegant helix and life's messy mutations are partners in this ballet, maybe the universe isn't just hospitable to life, maybe it's rooting for it. Earth spins through space with a rhythm so steady we set our clocks by it tilted just enough to gift us seasons, yet stable enough to avoid climatic freefalls into ice ages or infernos. This delicate balance hinges on symmetry, the sun's reliable rays, the moon's gravitational tug smoothing our orbit, the axial tilt locked at 23.5 degrees like a cosmic metronome. But beneath this orderly veneer, chaos thrums. A butterfly flaps its wings in the Amazon, and weeks later, a chain of atmospheric dominoes topples into a hurricane off the coast of Florida. Warm ocean currents shift by half a degree, and suddenly, crops wither or floodwaters rise. Earth's climate is a masterpiece of equilibrium, forever teetering on the edge of upheaval. Now compare this to Venus, our so-called sister planet. Both worlds formed from the same stellar nursery, similar in size and composition, but somewhere along the way, Venus spiraled into catastrophe. A runaway greenhouse effect turned its skies into sulfuric acid curtains, trapping enough heat to melt lead. Surface temperatures soar past 800 degrees Fahrenheit, hot enough to vaporize oceans that might once have existed. What went wrong? The symmetry shattered. Venus lacks Earth's plate tectonics to recycle carbon, no moon to stabilize its wobbles, and a thick atmosphere that traps solar energy like a suffocating blanket. The result is a world where chaos won, erasing any hope of balance. This cosmic contrast isn't just about two planets, it's a parable about fragility. Jupiter's great red spot has raged for centuries, a storm larger than Earth powered by chaotic fluid dynamics, yet constrained by the planet's rotational symmetry. Mars, with its wispy atmosphere, swings from dust-choked tempests to silent, frozen stillness. Even Saturn's hexagonal polar jet stream, a near-perfect geometric wonder, hides turbulent winds churning beneath. Everywhere we look, the same theme repeats. Symmetry sets the stage, but chaos writes the script. So what makes Earth different? The answer might lie in feedback loops, those delicate dials between stability and disaster. Take phytoplankton, microscopic ocean plants that produce half our oxygen. When water's warm, their numbers plummet, reducing cloud seeding compounds and amplifying heating, a vicious cycle. But on geologic timescales, weathering rocks pull carbon from the air, cooling the planet back down. It's as if Earth has built-in thermostats, a symphony of checks and balances fine-tuned over billions of years. Yet these systems aren't infallible. Ice core records reveal how past climate shifts happened not in smooth gradients, but in violent jerks, evidence of tipping points where symmetry buckled under chaos's weight. Today, as we pump greenhouse gases into the sky, we're conducting an unprecedented experiment. How much pressure can the system take before it snaps? Venus whispers a warning from across the void, while Mars stands as a frozen testament to what happens when balance fails. Perhaps climate isn't just a local phenomenon, but a universal language. The same physics that stirs Jupiter's storms shapes our jet streams. The same feedback loops that boiled Venus might lurk in exoplanet atmospheres light years away. If so, then Earth's climate is more than a weather report. It's a cipher for decoding how order and disorder dance across the cosmos. And as we peer deeper into alien skies, we might just find that the universe's greatest marvel isn't perfection or pandemonium, but the precarious, precious edge between them. Far beyond our solar system, worlds spin in perfect harmony with the laws of planetary motion, yet their surfaces tell stories of unimaginable extremes. Take Kepler 10b, a scorched rock orbiting so close to its star that its surface temperature rivals molten lava, or Ogle 2005 BLG 390 Lb, a frozen outcast where thermometers would shatter at -300 degrees Fahrenheit. These aren't the exceptions, they're the rule in a cosmos where orderly orbits and chaotic conditions exist side by side. The same gravity that sculpts their precise elliptical paths also twists their atmospheres into hurricanes larger than planets or locks entire hemispheres in eternal fire and ice. Consider tidally locked exoplanets, where one face perpetually bakes under stellar fury while the other languishes in endless night. At first glance, this seems like perfect symmetry, a cosmic coin forever fixed between heads and tails. But peer deeper and chaos emerges. On TRAPPIST-1e, supersonic winds might howl across the twilight zone, redistributing heat in violent torrents. On GJ 1214b, a steamy waterworld, global oceans could boil on the dayside while freezing into continent-sized icebergs on the other. These aren't static dioramas, they're roiling laboratories where the universe tests every possible combination of order and bedlam. The data streaming from telescopes like James Webb adds layers to this paradox. WASP-76b, a gas giant where iron rains from the sky, follows its orbit with clockwork precision, even as its atmosphere rips apart atoms into glowing plasma. K2-141b's surface is a churning magma ocean, yet its gravitational dance with its star could teach Newton a thing or two about celestial mechanics. Even rogue planets, untethered from any star, drift through the void along trajectories so predictable we can map their lonely journeys for millennia. What does this symphony of extremes reveal about cosmic design? Perhaps the universe is less interested in neat categories than we are. The same physics that carves a planet's path around a star also seeds the storms that ravage its skies. Gravity may be the conductor, but turbulence plays first violin. As we uncover more exoplanets, each one a unique experiment in balancing forces, we're learning that harmony doesn't require uniformity. A planet can obey every law of motion and still be a maelstrom, and that, in the end, might be the most profound lesson of all. The cosmos doesn't choose between precision and pandemonium. It thrives on both. Imagine a civilization so advanced it captures every photon of its star's energy, wrapping its sun in a vast, intricate web of solar panels, a Dyson sphere. This megastructure isn't just science fiction. It's a logical endpoint for any society mastering the laws of thermodynamics. The Kardashev scale, a method of ranking civilizations by their energy use, places such a culture at Type 2 capable of harnessing the total output of their home star. But here's the catch: even with that staggering power, entropy lurks like a cosmic tax collector. Energy can't be created or destroyed, only transformed, and every conversion, from sunlight to electricity to the glow of city lights, leaks waste heat into the void. The more a civilization consumes, the faster it dances toward thermal equilibrium, that distant future where all energy diffuses into a lifeless, uniform haze. This isn't just a theoretical problem. Right now, humanity straddles type 0 on the Kardashev scale, barely tapping into Earth's energy budget while grappling with the chaos of climate change. Our power grids, factories, and even smartphones radiate waste heat, a microscopic preview of the thermodynamic trap awaiting any growing civilization. The universe doesn't discriminate whether you're burning coal or antimatter. Entropy always demands its share. Advanced societies might delay the inevitable with Dyson swarms or black hole engines, but the ledger always balances. Heat death isn't a myth, it's the ultimate deadline written into the laws of physics. Yet within this grim equation lies a paradox. Entropy isn't just a destroyer, it's the engine of complexity. Stars shine because heat flows from hot cores to cold space. Life thrives on Earth because the sun's energy cascades through ecosystems, driving photosynthesis, weather, and evolution. A hypothetical Type 3 civilization commanding the energy of an entire galaxy wouldn't just fight entropy, it might sculpt it, channeling waste heat into new structures or even exploiting quantum loopholes to recycle energy. Some theories suggest such cultures could engineer closed time-like curves, essentially borrowing energy from their own future. Others propose they'd embrace a digital existence where consciousness runs on minimal thermodynamic cost. Which raises a haunting question. If entropy is universal, why haven't we found anyone else out there? SETI decades-long silence might hint at a great filter, a cosmic bottleneck where civilizations either master the symmetry-chaos balance or perish by it. Dyson spheres should glow in infrared, their waste heat detectable across galaxies. Yet our telescopes catch only whispers, not the roaring signatures of stellar engineers. Maybe advanced life is rarer than we thought, or perhaps they've transcended detectable energy use altogether, vanishing into substrates we can't yet imagine. The lesson is humbling. Thermodynamics doesn't care about ambition or intelligence. It's the great equalizer, reminding us that growth has limits, and even the mightiest civilizations must negotiate with chaos. Whether we're alone or not, the Kardashev scale isn't just a measure of power. It's a survival test and the passing grade, learning to thrive within the universe's strictest bookkeeping. What if the universe isn't just governed by symmetry and chaos, but programmed by them? The simulation hypothesis suggests our reality might be an advanced digital construct, with the laws of physics acting like lines of code in a cosmic software. In this scenario, symmetry wouldn't just be a natural principle, it could be an optimization trick, a way to reduce computational load by reusing elegant mathematical patterns. Chaos, on the other hand, might be a built-in feature to keep the simulation dynamic and unpredictable, like procedural generation in a video game. Think about quantum mechanics, where particles exist in fuzzy superpositions until observed. Could this indeterminacy be the simulation's way of rendering only what's necessary, like a graphics engine loading details as you explore a virtual world? Philosophers like Nick Bostrom argue that if civilizations ever reach the technological capacity to run ancestor simulations, hyper-realistic recreations of their past, the statistical likelihood we're living in one is surprisingly high. After all, why wouldn't future societies create countless simulated worlds, making the odds of us being in the original reality vanishingly small? But here's where symmetry and chaos get eerie. The mathematical elegance of the universe, the golden ratio in spiral galaxies, the fractal branching of trees, even the way light bends around stars, could reflect the efficiency of a master programmer. Just as a coder uses loops and functions to avoid redundant work, nature might reuse symmetrical templates to conserve computational resources, yet chaos keeps things interesting. Glitches in the system like quantum tunneling where particles teleport through barriers, or dark energy's inexplicable acceleration of cosmic expansion might not be bugs at all. They could be intentional randomness, ensuring the simulation doesn't become predictable or stagnant. Even human consciousness, with its messy blend of logic and emotion, might be a feature designed to generate novelty within the program. After all, what's the point of a universe without surprises? Critics dismiss this as sci-fi, but the debate rages in academic circles. Physicists have proposed experiments to test the hypothesis, like hunting for pixelation in the fabric of spacetime or anomalies in high-energy particle collisions. Others point out that if the simulators wanted to hide their work, they'd erase such clues, making the hypothesis unfalsifiable. But whether you buy it or not, the idea forces a radical rethink of reality's scaffolding. If symmetry and chaos are parameters in a cosmic code, then the universe isn't just mysterious, it's meta. And that changes everything from how we do science to what it means to exist at all. Time crystals sound like something straight out of science fiction, yet they're one of the most mind-bending discoveries in modern physics. Imagine a clock that ticks forever without any batteries, or a snowflake that never melts but keeps changing its shape in a perfect, repeating dance. That's essentially what a time crystal does. It's a quantum system that oscillates indefinitely without any energy input, defying one of the most fundamental symmetries in nature, time translation symmetry. Normally, if you have a system in equilibrium, like a pendulum at rest or a cup of coffee cooling to room temperature, it eventually settles into a stable state. But time crystals refuse to play by those rules. They're perpetually in motion, locked into a rhythm that never winds down, like a cosmic heartbeat that doesn't need a heart. The idea was first proposed by Nobel laureate Frank Wilczek in 2012, and at the time, many physicists dismissed it as impossible. After all, perpetual motion machines violate the laws of thermodynamics, right? But time crystals aren't breaking those laws, they're bending them in a way no one expected. Instead of burning energy to sustain their motion, they exploit quantum weirdness to stay out of equilibrium forever. Picture a row of magnets arranged so that their spins flip in a repeating pattern, not because they're being pushed, but because the system's quantum ground state forces them into an endless loop. It's order emerging from chaos, not despite it, but because of it. What makes time crystals so revolutionary isn't just their defiance of equilibrium, it's what they reveal about the fabric of reality. Symmetry breaking is a cornerstone of physics, from the way ice crystals form to how the Higgs field gives particles mass. But time crystals break symmetry in a whole new dimension, time itself. While most crystals like diamonds or salt have atoms arranged in repeating spatial patterns, time crystals add rhythm to the mix, oscillating between states with perfect, unshakable periodicity. This isn't just a new phase of matter, it's a new kind of phase, one that could rewrite our understanding of everything from quantum computing to the early universe. Labs around the world are racing to unlock their secrets. In 2017, researchers at Harvard and the University of Maryland created the first verified time crystals using chains of ytterbium atoms and diamond defects, respectively. These weren't theoretical curiosities, they were real, observable systems ticking away like quantum metronomes. Now, scientists are exploring whether time crystals could exist naturally in extreme environments, like the crushing pressures of neutron stars or the seething plasma of the early cosmos. Some even speculate that dark matter, that elusive cosmic glue, might have time crystalline properties, ticking unseen in the voids between galaxies. But the most tantalizing question is whether time crystals hint at deeper cosmic rhythms. If matter can encode time into its very structure, could the universe itself have hidden cycles we've yet to detect? Ancient cultures spoke of great years and cyclical time, while modern physics grapples with entropy's arrow. Time crystals sit at the crossroads, offering a glimpse of a reality where time isn't just a one-way street, but a spiral, a loop, or something stranger still. As we probe deeper, we might just find that the universe's most profound symmetries aren't in space, but in time, and that the ticking of these quantum clocks could be the key to hearing its hidden music. Gravitational waves are the universe's way of whispering its deepest secrets, ripples in the fabric of space-time itself, born from the most violent symphonies of chaos and symmetry. Picture two black holes, each a perfect sphere of warped gravity, locked in a final, frenzied dance. As they spiral toward collision, their immense masses churn the surrounding space-time like a spoon stirring honey, sending out waves that travel at the speed of light. By the time these ripples reach us, they're vanishingly faint, stretching and squeezing space by less than the width of an atomic nucleus. Yet within those subtle tremors lies a story of cataclysmic beauty, a merger so violent it momentarily outshines every star in the observable universe, yet so precise it follows Einstein's equations to the letter. When LIGO, the Laser Interferometer Gravitational Wave Observatory, first detected these waves in 2015, it wasn't just a triumph of engineering, it was a revelation. For centuries, astronomy relied on light, from Galileo's telescope to Hubble's deep field images, but gravitational waves are something radically different. They're not photons streaming through space, they're the very geometry of reality vibrating like a drumhead, and what they've already told us is staggering. The chirp of merging black holes, a rapid rise in frequency as they spiral inward, reveals their masses, spins, and even how fast the universe is expanding. Some collisions hint at black holes born from earlier mergers, cosmic matryoshka dolls hiding within event horizons. Others, like the neutron star collision observed in 2017, solved mysteries like the origin of gold and platinum, proving these heavy elements are forged in the furnaces of chaos. But the real magic lies in the paradox. Black holes are the simplest objects in existence, describable by just three numbers: mass, spin, and charge. Yet when they collide, their event horizons twist into chaotic, asymmetrical shapes before settling back into perfect smoothness. It's as if the universe is reminding us that even in its most extreme moments, symmetry isn't lost, it's temporarily disrupted, like a pond's surface ruffled by a stone. And these disruptions are anything but random. The waveforms LIGO captures match theoretical predictions with uncanny precision, a testament to how deeply order underlies even the wildest cosmic events. What's next for this new era of listening to the cosmos? Future detectors like the space-based LISA mission or next-generation ground observatories will tune into lower frequencies, catching the mergers of supermassive black holes, monsters weighing billions of suns. Some theories suggest we might even detect echoes from the Big Bang itself, primordial gravitational waves imprinted on space-time in its first trillionth of a second. Others speculate about exotic sources, cosmic strings, hypothetical defects in space-time left over from the universe's infancy, or even collisions between higher dimensional objects predicted by string theory. Gravitational waves don't just add another sense to our cosmic toolkit, they rewrite the rules of observation. Light can be blocked by dust or bent by gravity, but space-time ripples pass through everything, carrying undistorted messages from the edge of black holes and the dawn of time. In their subtle vibrations, we're not just hearing the universe's stories, we're feeling its heartbeat. Deep beneath the equations governing our universe lurks a chilling possibility that everything we know, from atoms to galaxies, exists in a precarious state of balance, like a marble resting at the top of a hill. This is the nightmare scenario of vacuum decay, where the very fabric of reality could suddenly rewrite itself in a wave of destruction spreading at light speed. The culprit, the Higgs field, the invisible energy blanket that gives particles their mass. Most of us think of it as stable, but some theories suggest it might be metastable, like a frozen lake that seems solid until a single crack triggers a catastrophic shattering. If the Higgs field were to suddenly drop to a lower energy state, it wouldn't just tweak physics, it would erase the current rules entirely. The laws governing symmetry, chaos, even the speed of light could be overwritten in an instant, leaving behind a universe unrecognizable to science, or worse, lifeless. Imagine a bubble of true vacuum forming somewhere in space. Inside this bubble, the Higgs field settles into a deeper, more stable configuration, releasing unimaginable energy as it does. The walls of this bubble expand outward at the speed of light, rewriting physics as they go. Stars, planets, and even the empty void ahead of the wave would vanish into a new reality before anyone could blink. There'd be no warning, no time to react, just an abrupt end to the universe as we know it. The terrifying part, this isn't science fiction. The math checks out. Particle colliders like the Large Hadron Collider have probed the Higgs boson's properties, and while the data suggests our vacuum is likely stable, the margin for error leaves room for doubt. We might be living on borrowed time, with the ultimate cosmic reset button hovering just outside detection. What's even stranger is how this ties into symmetry and chaos. The Higgs field's current state is a relic of the early universe, frozen in place during the chaotic aftermath of the Big Bang. Its symmetry breaking is what gave particles mass, allowing atoms, and eventually life, to exist. But if that symmetry were to break again, collapsing into a deeper equilibrium, the delicate balance between order and randomness would vanish. No more galaxies spinning in majestic spirals. No more quantum fluctuations sparking new stars, just a uniform, lifeless void governed by completely different rules. Could this have already happened elsewhere? If a vacuum decay bubble began in some distant galaxy billions of years ago, its light speed expansion would still be en route to us, invisible until it arrived. Some theories even suggest that the universe's accelerating expansion, driven by dark energy, might make such an event more likely over time, as the stretching of space strains the Higgs field's metastability. It's a sobering thought. The very force pushing galaxies apart could be nudging us closer to oblivion. Yet for all its doom and gloom, vacuum decay isn't just a cosmic horror story. It's a mirror held up to the universe's fragility. The fact that we can ponder it at all is a testament to the improbable stability we enjoy, at least for now. Every second we exist is a defiance of entropy and chance, a fleeting moment where symmetry and chaos conspire to keep the cosmos recognizable. Whether that balance lasts another trillion years or shatters tomorrow is one of physics' greatest unanswered questions, and perhaps that's the most unsettling part. The universe doesn't owe us permanence. It merely allows it for now. Watch a flock of starlings twist and turn as one, their movements so synchronized they seem telepathic. Yet there's no conductor guiding this aerial ballet, just three simple rules hardwired into every bird. Stay close to your neighbor, match their speed, and avoid collisions. Multiply these tiny decisions by thousands, and suddenly, chaos gives way to breathtaking harmony. This is emergence in action, the universe's favorite trick for conjuring complexity from simplicity. From the firing patterns of neurons in your brain to the swirling arms of spiral galaxies, the same phenomenon plays out everywhere. Simple ingredients following basic rules create patterns so intricate they appear designed. But the magic isn't in the pieces, it's in how they interact. Take neurons, for example. A single brain cell isn't intelligent, it just fires electrical pulses when stimulated. But connect billions with the right feedback loops and consciousness emerges. Memories form, ideas spark, and somehow, this network of biological switches becomes you. No single neuron understands Shakespeare or recalls your first kiss, yet together, they create a mind capable of pondering its own existence. The same principle shapes ant colonies, where workers with no master plan build elaborate tunnels and farms through countless tiny interactions. Even the internet, a vast, sprawling entity, self-organizes from the simple protocols governing data packets. Now zoom out to the cosmic scale. Galaxies don't form because some celestial architect arranges them. Gravity, acting on tiny density fluctuations left over from the Big Bang, pulls matter into vast webs. Over billions of years, these clumps spin, merge, and settle into the majestic spirals and ellipticals we see today. The rules are straightforward. Mass attracts mass, yet the results are endlessly varied, no two galaxies alike, each a unique fingerprint of initial conditions and chaotic interactions. The universe isn't sculpting these structures, they're emerging from the bottom up like a sand dune organizing itself grain by grain. This raises a profound question. Could the universe itself be an emergent phenomenon? Some physicists speculate that spacetime and even the laws of physics might not be fundamental. Instead, they could arise from something deeper, perhaps a network of quantum information, like pixels on a cosmic screen. Think of how temperature emerges from the motion of atoms. Individually, molecules don't have a temperature, but collectively, their kinetic energy creates this new property. Similarly, what we call gravity or electromagnetism might be surface-level descriptions of processes we haven't yet uncovered. Even time's arrow, the relentless march from past to future, could be an illusion born from entanglement in a timeless quantum substrate. The hunt for these deeper principles is reshaping science. Researchers simulate virtual universes on supercomputers, tweaking initial rules to see if familiar physics emerges. Others explore holographic duality, where our three-dimensional reality might be encoded on a two-dimensional boundary, like a DVD storing a movie. String theory's extra dimensions and loop quantum gravity's spacetime atoms are also attempts to find the simple rules beneath the cosmic complexity. But here's the catch. Emergence isn't just a theory, it's a puzzle about puzzles. If our brains are emergent phenomena, can they fully grasp the mechanisms that birthed them? Perhaps the answer lies in the patterns themselves. Fibonacci sequences appear in sunflowers and spiral galaxies. Fractals repeat in coastlines and lightning bolts. The universe seems obsessed with certain mathematical motifs, hinting at universal principles waiting to be decoded. Whether we're close to grasping them depends on how deep the rabbit hole goes. One thing's certain, every time science peels back a layer of reality, it finds not chaos but new forms of order, suggesting that emergence isn't just how the universe works. It might be what the universe is. As we've journeyed from the quantum realm to the cosmic web, one truth shines brighter than any star. The universe doesn't choose between order and chaos, it thrives on their partnership. Think of a snowflake's perfect symmetry forming from turbulent air, or a galaxy's elegant spiral emerging from primordial turbulence. These aren't contradictions, they're collaborations. The same quantum uncertainty that makes particles unpredictable also allows atoms to bond, creating the stable matter that builds worlds. The gravitational chaos that stirs nebulas into stellar nurseries follows precise mathematical laws as it does so. Even life itself, that improbable spark, depends on DNA's strict helical code being flexible enough for random mutations to drive evolution forward. This cosmic waltz between predictability and surprise might hold the key to existence itself. Too much symmetry, and the universe would freeze into static perfection. No stars, no planets, no change. Too much chaos, and structure would dissolve into formless noise. But in that narrow, shimmering band between them, reality finds its rhythm. Supernova scatter heavy elements while gravity gathers them into new solar systems. Quantum fluctuations birth galaxies while dark matter's invisible scaffolding holds them together. The universe isn't just tolerating disorder, it's harnessing it, using chaos as a sculptor uses a chisel, revealing forms hidden in the marble of possibility. What does this mean for us, these fleeting constellations of atoms pondering the vastness? Perhaps we're not just observers, but participants in this grand experiment. Every thought we have emerges from neurons balancing electrical order and noisy randomness. Every civilization we build teeters between structured progress and creative disruption. Even our search for cosmic understanding mirrors the universe's own dance, imposing patterns through mathematics, while embracing the unknown with each new discovery. So as you gaze at the night sky tonight, remember, the same forces that whirl in distant galaxies pulse through your own cells. The tension between symmetry and chaos isn't just out there, it's the very rhythm of existence from quark to quasar. And if we're here to witness it, that might be the most beautiful symmetry of all. Share your perspective in the comments where you see this dance playing out in your world. For more journeys to the edge of understanding, hit subscribe. Until our next cosmic adventure, stay curious. The universe has only begun to reveal its secret.